Hello everyone, welcome back. Today we will be talking about optimization. What that means is you have a function and you want to find either the minimum or the maximum of the function. So optimization is kind of a generic word for either minimizing or maximizing. Before we talk about that, I want to discuss a related problem which is called root finding. And here's how the problem works. We have some function g of x, so x is the input and g of x is the output. Here on the horizontal axis we have x, and the vertical axis is g of x, and then this magenta curve indicates the function. The root finding problem is that we want to find the x such that g of x equals 0. So you could look at that and say, well, this is an easy problem. It's just right there. But in practice, this is a bit more complicated than it looks. And the reason is that we don't really get to see the whole function. What you really get to see is a sequence of inputs and outputs. So what you would get to see is you get to basically guess the root x1, evaluate the function g of x1, which would give you this point here. And then from this point, you've basically got to guess which direction to move. So if you maybe guess right here for the next point, then you're going to be going in the wrong direction because the value of g of x went up, whereas you want it to go down to get to the root. But you didn't know that. All you had was this information, so you had to guess either way. So in this case, we guessed wrong and it went up. So our next guess, we're going to guess over here. And it's too low. So you could see that, if we had the access to see what this function looks like, you could just point to the root. But in reality, what we have to do is pick a sequence of input locations and then try to reconstruct the function and guess where the root is. So you'd probably think on the next turn, I'm going to pick something between these two and maybe right here, and we'll get pretty close. And then we can refine as we go. If we're lucky, we also know the derivative of the function g. So here's how I'm representing the derivative. So here's x1, and not only do we get to see the value of g, which is the height of this point, we get to see what its derivative is, which is what its slope is. So I'm representing the slope with this kind of short line. So if we knew the derivative, then we're going to eliminate this bad guess because we don't think that the root is going to be over here because it's going down in this direction. So we might guess a point on this side as our second guess, and we get here. And then we see it's to the right of the root, so the derivative is going to be going up, and we'll refine our guess and maybe get closer on the third one if we knew the derivative. So the root finding problem is finding the root, the value of x, for which the function is 0. But what you get to do in practice is evaluate the function and possibly its derivative at a sequence of points, and then iteratively try to get closer and closer to the solution. So that's how root finding works numerically. So what we're going to talk about next are specific algorithms for deciding what the next point you're going to guess is based on the information you have so far. And the most famous root finding algorithm is called Newton's method. So Newton's method is a method that requires knowledge of not just the function you're trying to find the root of, g, but also you have to be able to calculate its derivative. And we'll see an example of this in just a minute. So here's the algorithm. It's actually very simple. You start with an initial guess, x1, so I'm representing that here. And then you calculate the value of g, which again is the height, and then the value of the derivative of g, g prime, which is its slope. And basically you take this point and form a straight line that goes through the point and matches the derivative at the point. And then you follow the line down to where that line has its root. And then that's going to be your updated point. So in math, the way this works is once you have g of x1 and g prime of x1, you form its linear surrogate, which is just a fancy way of talking about this line. If you remember from algebra class, this would be point slope form of the line. So L is our linear surrogate, and it's just g of x1, which we calculated, and g prime of x1 times x minus x1. So this we're viewing as a function of x. This is our linear surrogate of x. And then we find the root of this function, and that's just easy algebra. We set the line to 0, and then we rearrange, and we get x2 equals x. So finding the root means setting it to 0, and then the root is we're going to call that x2. That's going to be our next guess. And if you just rearrange, the update is x1 minus g over its derivative, evaluated at x1. And then you just keep repeating this until g of xi, which is the value of x on the ith iteration, is close enough to 0. So in a picture, we draw this line that goes through the point and matches its derivative. Our next guess is x2, and we do the same thing. We calculate g of x2, calculate its derivative, draw the line that goes through the point and matches its derivative, and then our updated point is going to be x3, and then we just keep iterating until g is close enough to 0. All right, so it's very simple. It's just about approximating the function with a sequence of lines until you get closer and closer to the root. So let's just see how this works in an example. This is actually a very famous example that was discovered in ancient history, but it actually is an example of Newton's method, which is, of course, described much later. So here's the problem. Calculate the square root of 7. So if you think about this, this is equivalent to finding the x such that x times x minus 7 equals 0. Because if you just rearrange this, this would say x squared equals 7, which means that x equals square root of 7. And I'm just plugging in 7 to make it concrete, but you can use this to find the square root of any number. So our function is g of x equals x squared minus 7. Calculating its derivative is easy. It's just 2x. And then we just, here's our update formula. The next value of x is the current value minus g of x divided by g prime of x. And if you rearrange this, you don't need to rearrange it. It's this formula. So this is called the Babylonian method. Okay, and this works really well. So let's switch over to R, and we will show how this works. Okay, so I've defined the function g here, and I'm giving it two inputs. X is going to be x as it was in the previous page, and k is the function that we want to calculate the square root of. So we're going to start, you can see down here, we're going to set k to 7, but we can try this for other numbers. And that's just x squared minus k. And then g prime, which I'm writing as g1, is just 2 times x. Remember that if you don't include a return statement, the function is going to just return the last thing that's evaluated. So here the function is just going to return x squared minus k. Okay, so let me define those two functions. I'm going to set k to 7, and I have to give a starting value. So how would I pick a starting value? Well, I know 2 squared is 4, and I know 3 squared is 9. So probably best to pick a number between 2 and 3, but I'll just pick 2. And what I'm going to print out here is I'm using the sprintf function to print out x and x squared to a bunch of digits. So that's x, and that's x squared, as expected. And then I'm just going to iterate. So the iteration is I'm going to do x minus g over g prime, and then I'm going to print out the value of x on each iteration. So let me run this. And you could see here's the first value we tried. Based on that information, it guessed that the square root is 2.75. If you square that, you get 7.5625. Let me make this a little bigger. So the second guess was 2.75. You square that, you get 7.5625. And then it updated to 2.6477. That's even closer. Square of that is 7.01. Did another update, and then now it's gotten really close. It's correct to 5 decimal places. And then the next update is basically exact. It's correct to at least 9 decimal places. So this thing finds the square root very quickly. And just for fun, we can try some other guesses. So let's actually make it work poorly. Actually, let's make it break. So what's going to happen here, if we set x to 0, g prime of x will be 0, and you're going to try to divide by 0, and it's going to break. But obviously 0 is going to be a bad guess for the square root, but we'll run that. Okay, it registered infinite, which makes sense. So let's give it just a little push, set it to 1. So it makes a really bad guess on the second one, but then it realizes it did a bad job and it gets closer and closer. And by iteration 9, it's basically found it. So it takes longer to converge with a bad starting value, but eventually it gets there. So let's give it like 1. 1's pretty far away, but it's still going to find it quickly. Took about 5 or 6 iterations. Okay, so that works really well. Let's go back to the notes. All right, so that's an example of Newton's method of root finding. And you could see when it works really well. But of course, if you give it a really bad starting value, it can fail. And for some functions, it will fail sometimes too. But when it works, it really works. It converges very quickly. Now let's get to the problem that we introduced at the beginning, finding the minimum or maximum of a function, which is optimizing a function. And as stated, the problem is find the x such that f of x is at the minimum, which means that f of x is less than or equal to f of x star for any other x star. So in a picture, here's our function f of x. We want to find the point at which f attains its minimum, which is somewhere around here. So why does this matter for statistics? This is a really important problem in statistics. If you've heard of least squares, that's an optimization problem. More generally, there's a technique called maximum likelihood estimation. So that's the problem of finding the maximum of the likelihood function, which is equal to the probability density function with respect to the parameters, or equivalently finding the maximum of the log likelihood function. So one way of solving this problem of finding the minimum or maximum of a function is to convert it to the root finding problem. So that's the reason we introduced the root finding problem first. So the way that works is you find the x such that the derivative of x equals 0. And for the minimum, that would mean that the second derivative is positive. So converting f to its derivative might look something like this. And the point at which it reaches its minimum is the point where the derivative is 0, which is right here. Okay. So there's a corresponding Newton's method for minimization, which is basically, well, it's exactly Newton's root finding method, but applied to the derivative of the function that you're trying to minimize. So it works exactly the same way. You have an initial guess, x0, and then you set x1 equal to x0 minus the derivative divided by the second derivative. And then now you have x1, then you update x2 and keep going, and then you repeat until the derivative is small enough. And of course, at the end, you have to check that you found a minimum, by checking the f double prime x is bigger than 0. So this is exactly the same algorithm, except instead of g, you're using f prime, and instead of g prime, you're using f double prime. All right, so let's look at an example. Here's kind of a weird function. F of x is e to the 2x minus 4 plus e to the 2 minus x. And I'll show you the actual plot, but it's going to look something like this. And actually, the root is going to be a little bit to the right of 0. What I plotted in gray, this is roughly e to the 2x minus 4, and this is e to the 2 minus x. So the sum of those is the magenta line. All right, so exponentials are easy to differentiate. So this is 2e to the 2x minus 4 minus 2e to the 2 minus x. And here's the second derivative. And then, therefore, this is the update formula. It's xi minus first derivative. And, of course, this should say xi here. We have to plug in the current value. And this should say xi here. So that's the update formula. So let's go back to the R code and we'll implement this. So here I'm defining f, and now I need to define both the first and second derivative. That's f1 that we just calculated, and that's f2. And just to visualize the function, I'm defining x to be a sequence of numbers between 2 and 4. And we'll plot x and f. So that's what the function actually looks like if we plot it on a computer. The minimum is going to be somewhere around here, 1.8, 1.9. And in this case, I'm going to keep track of the updates for x. So I'm defining a vector x with 10 elements. And I'm going to start with a guess of 0. So I'm going to store the first guess. And then each time I'm going to plot x and f of x. And then here's my update. It's the same thing. You take x, j minus 1 minus first derivative divided by second derivative. And I'm going to plot out, or I'm going to print out the value of x and f of x. All right, so let's run this. So here's our starting value of 0. Here's the value of f of 0. Our next guess is 0.98. This is good because the value of f went down. Our next guess is 1.74. It went down even further. And then we start to get really close to the answer. So here, it's basically the answer within, it's near the minimum within, I guess, 6 decimal points. And then, of course, we get closer and closer as we continue to iterate. All right, so this found the minimum in basically 1, 2, 3, 4 steps. So it's very fast again. And then I'll just plot. So here's the function. And then here's the sequence of points that we tried. That was our initial guess. Then it tried 0.98. And then basically after that, it's very close to the minimum. Okay, so again, this works very quickly when the function is nice. And once it converges really fast. Okay, so that is Newton's method for minimization when you're trying to minimize a function of a single variable. All right, so in some cases, we either can't or don't want to apply Newton's method exactly as stated. One reason is we might have a formula for calculating the derivative of f prime of x, but it might be too complicated to calculate the second derivative. This could be because the math is too hard, or what comes up often in practice is it's too computationally demanding to calculate the second derivative. All right, so if you're in that situation where you can get f and f prime but not f double prime, you're not completely out of luck. So if you look at this picture, basically in your initial guess, you know f of x and you know the derivative of f of x. So you know, if you're trying to find the minimum, you know that the minimum is probably going to be somewhere to the right because it's going downhill at the initial guess. But if you don't know the second derivative, it makes it hard to guess how far to move. So what I plotted here are two different functions that match f of x and f prime of x, but have two wildly different minima. So the gold one has a minimum around here, and the green one has a minimum way off the page. So what makes this problem hard is you don't know how far to go. If you knew the second derivative, you could try to narrow down between which one of these you thought it was because you'd know the curvature at the point. And then you'd have a better guess for the next point. But if you don't know the curvature, basically you just know it's downhill, and the minimum could be way off the page or it could be right next to it. Here's what the derivative looks like. So I'm just taking the derivative of this. Here the gold one gets to the root quicker, whereas the green one takes much longer. So we know this is a case where we know what direction to move in. We should move to the right, but we don't know how far to move because we don't know the curvature of the function. So basically what we need to do is guess and check. So here's what the updates look like. xi plus 1 equals xi minus f prime of xi. So we're moving in the direction of minus f prime, but we have to move by some amount, and we have to guess how far to move. So in general, this kind of method is called gradient descent. In one dimension, you could really just call it derivative descent. We'll look at the multivariable problem in a minute. And then there are various algorithms for guessing how far to move. And so I'm just going to give you one of them, but you can dream up your own, or you can, or there are other ones out there. So here's one. We start with we have our value of x, and we can calculate f prime. And we just pick a value of c. And then we calculate the derivative of xi minus f prime x. So derivative of f at the next point, given that value of c. If it has the same sign, then we're in this situation. So we start here, and if it has the same sign, that means we need to move a little further. So we'll just double the value of c. And if we double it, we get to here. And now the derivative is positive. And so we know that the root should probably be between this one and this one. So we just do a linear surrogate and make this one the next guess. Yeah. Now, if the sign does change, so if our first guess is here, excuse me, if our first guess is here, then we've gone too far. And so we need to cut c in half until we get back on the other side. So we have 2 points straddling the root, and then we just take a linear surrogate here. So there's various methods for doing this. This is just one kind of simple way to do it that will eventually bring you to the root. All right, now we move on to the maybe more interesting problem, which is the optimization or minimization of multivariable function. So you've already seen this actually in linear regression. So here's an example. This is the sum of squares criterion. So we observe y1 up to yn. These are the responses. And for each response, we have a set of p plus 1 covariates, xij. And we want to estimate the regression coefficients, b0 to bp. And the way we estimate them is we form the sum of squares criterion, and we pick the b's to minimize this criterion. So the word minimizes is there, or least means to minimize. So this is an optimization problem. Now, for multiple linear regression, we don't have to bother with Newton's method because there's actually a formula that tells you what the minimum is. But you could apply Newton's method to this. but we're going to need a multivariable version of this because we're minimizing f over a vector of regression coefficients. Another example that we'll look at in a minute here is what I mentioned before, maximum likelihood estimation. So again, we observe some responses, y1 to yn, and then we have some model for the responses. And I'm just representing that by saying we're going to model yi with a set of independent random variables, capital Yi, that have some probability density p. So p is a univariate probability density modeling the ith value of y. And that probability density, its argument is z, but it depends on a number of parameters, theta 1 up to theta k. So this is equivalent to maximizing what's called the log likelihood function. So the likelihood function is just since they're independent, it's just the product of the densities evaluated at the data. And of course, the log of the likelihood is just the log of that. And if you take the log of the product, you get the sum of the logs. So in maximum likelihood estimation, we're maximizing this quantity here. So it's the log of the probability density function evaluated at the data, viewed as a function of the parameters. So we're trying to pick the parameters that make the data most likely. So this is in statistics, this is most often where you see optimization come up. This is a very commonplace. So just to show this in a picture, here's a case where we have two parameters. The log likelihood function might look something like this, where this is the maximum here. And of course, you can always turn this into a minimization problem. If you want to maximize the log likelihood, you just want to minimize the negative log likelihood, which is usually how it's done in practice. Okay, so there's going to be a version of Newton's method for these multivariable functions, but we have to define what we mean by the first derivative and second derivative of a multivariable function. So you should have seen this in your calculus course, but we're going to just review it very quickly. Okay, so in the above examples, the inputs were here regression coefficients and parameters in a model, so b and theta. We're going to go back to just making the inputs called x. So that's our generic input to a function f. So x is a vector input, x1 to xk. And the output of f is going to be a scalar. So input vector, output scalar. And we want to minimize that scalar. So what do we mean by the first derivative? So the first derivative of a multivariable function we're defining as a quantity called the gradient. And all that means is we take the derivative of f with respect to each input separately and stack them in a vector. And then the notation we use is this partial derivative notation. All this means is you just view f as a function of the first input, x1, take the derivative with respect to that, and put it in the first entry of the gradient. So if we look at our example of least squares, and I'll just do simple linear regression. So there's just an intercept and a single linear term here. If we take the gradient of this, that means with respect to the input b, in the first entry we take the derivative of this function with respect to b0. So it's going to be 2 times this times minus 1 because there's a negative on b0. So that goes here. And then we take the derivative with respect to b1. So again, it's going to be 2 times this times minus x1. So we get this. So this is what the gradient looks like for the simple linear regression. Okay. As before, there's a method called gradient descent. So the way this works is basically you have a starting input. So this is a vector, and so the notation here is slightly confusing. Here I mean a vector x, and I'm talking about the ith vector that we've chosen, which is different from the ith value of x itself. So if there's an underline, that means it's actually a vector, but we need to index them because we're going to be updating. So given that, we compute the value of the function and its gradient. So this is going to be a scalar. This is going to be a vector. So if you're looking at this example here, if this is our initial guess, so we've calculated the value of the function, which is the value of the contour here. And then the gradient is going to be a vector and pointing in some direction. So the arrow represents our gradient. And the way gradient descent works is basically you extend that arrow and pick a point along that extension of the gradient, and that'll be your updated point. So here we set xi plus 1 to be xi minus the gradient times a constant. So the constant is how far you move along the gradient. And we make sure we choose the constant so that the new value of the function over here is smaller than the previous value. And again, there are various ways of trying to do this. But essentially what it comes down to is for each iteration, you do a one-dimensional minimization over this amount to move c. So the idea is here, you're trying to move downhill on each step. And eventually, if you keep moving downhill, you're going to get closer and closer to the minimum. And then you stop when your gradient gets close to 0 or the function stops getting smaller. Okay, so like I said, what that means is if you move along the gradient, that guarantees that you're kind of going downhill. But it's not actually the optimal direction to look in many cases. So if we go back to this example, the gradient points this direction. But actually what you would rather go is this direction, which will point you closer to the minimum. All right, so that's what Newton's method is going to do. But before we get to Newton's method, we have to talk about the second derivative of a multivariable function. So what Newton's method does, it tries to find a better direction to search in, and it tells you how far to move along that direction. So we're not going to have to do this kind of interior optimization over how far to move when we're using Newton's method. Okay, so what is the second derivative of a multivariable function? We call that the Hessian. And what that means is we're basically taking the gradient of the gradient. So if our input function is multivariable, the first derivative of that function is the gradient. That's going to be a vector. And the second derivative, the gradient of the gradient, is going to be a matrix. So basically the way this works is we're taking the gradient of each entry of the gradient. So let's just look at the first row. So in the first row, we're taking the derivative of partial f partial x1 with respect to each input variable. So along this first row, it's going to be the gradient of partial f partial x1. Second row is the gradient of partial f partial x2. So that just means the derivative of that thing with respect to each entry of x. So this is going to be, if x is the length k input, then the gradient, the Hessian, which has this upside down triangle squared f of x, is going to be a k by k matrix. So if that's just too much notation, let's look at our example of least squares. So let's go back and remind ourselves. This is the gradient of least squares. So to get the second derivative, what we're going to do is take the derivative of this with respect to b0. That's the 1, 1 entry. Then we're going to take the derivative of this again, but with respect to b1. That's going to be the 1, 2 entry. And then we'll take the derivative of this with respect to b0. That's the 2, 1 entry. And then we'll take the derivative of this with respect to b1. That's the 2, 2 entry. Okay. Maybe we can make this smaller so we can see both. Not going to fit. But okay, let's just do this. If you take the derivative of this with respect to b0, basically you're just going to get a minus 1 in here. So this is going to be minus 2 times sum minus 1. If you take the derivative with respect to b1, you're going to get a minus x inside of here. Take the derivative here with respect to b0, you're going to get a minus 1 in here, but you're left with the x. And then if you take the derivative of this with respect to b1, you're going to get a minus x times x. Okay, so that's this here. So that's the minus 1, the minus x, and the x squared. And if you just write this in terms of notation, this is going to be 2n. This is 2 times the n times the mean of x, and that's the same. And then this is 2 times sum xi squared. So this should be a plus actually. Okay. And the next thing is to note the symmetry of the Hessian. If you take the derivative of this with respect to xi, it's going to be the same as the derivative of this with respect to xj. So the notation we use for these entries is not usually this notation. So this is helpful for explaining what's actually happening, but we use this notation. All right, and that allows us to define Newton's method for multivariable functions. And it's very simple. Given a value of x, we compute f, its gradient, and its Hessian. And then the update is just this very simple formula. Xi plus 1 equals Xi minus. You take the Hessian, and then you take its inverse, and multiply that by the gradient. So if you think back to the original Newton's method, this is actually a very similar formula. Basically, in Newton's method, it was for univariate functions, it was derivative divided by second derivative. And this is basically the same thing. It's the inverse of the second derivative times the derivative. So this actually does reduce to the original Newton's method in one dimension. And what generally ends up happening with Newton's method is you get better search directions, and it also tells you how far to go, so you don't have to guess how far to go. And you generally will converge more quickly. All right, now there are an endless number of variations on Newton's method, and for various reasons, it could be helpful to replace or modify the Hessian matrix. So sometimes you may get a step direction that's just kind of wild. So we actually saw that in one dimension with the starting value of 0 for the square root. We got a kind of a wild infinite step direction. So obviously that's not the right thing to do. And so we may want to kind of regularize the step direction. So there's these various modifications to Newton's method. Generally, they're called Quasi-Newton's method, and they usually proceed by replacing the Hessian matrix or modifying it in some way. So the first one is pretty simple. If we replace the Hessian with 1 over a constant times the identity matrix, this becomes gradient descent. So if we look at the update formula, it's this minus this inverse. Well, okay, we have the identity here, so that goes away. 1 over c inverse is just c, so this just becomes gradient descent. There is a method, I think it's called fractional Newton, where basically if you divide the Hessian matrix by a constant, you'll take smaller steps. So that can be a safer thing. So just take 1 over c times the Hessian. This comes out as c. So we'll take a step size. So this would be the step, but if we multiply it by c, we're going to get a different size step. So this is, sometimes we'll do this and we'll set c to like a half to make sure we take smaller steps. Some people will add a diagonal to the Hessian. So this is, I don't know if there's a name for this. I would call it a regularized Newton method. Basically, you add a small value to the diagonal of the Hessian. And what ends up happening in practice here is, so here's our little plot. So this is the gradient. This is the Newton step, the full Newton step. A fractional Newton would only go part of the way and then proceed from there. What ends up happening when you add a diagonal, it kind of interpolates between the full Newton step and the gradient step. So this can be kind of a safer thing to do sometimes. In some cases, just like before, it may be too expensive to calculate the Hessian, or it may be too analytically difficult to figure out what the second derivatives are. And in those cases, we can try to approximate the Hessian using gradient information. I'm not going to go into detail on how or why this one works, but this is a popular one that's implemented in R called the BFGS algorithm. So basically, you have your given a value of x and a guess for the Hessian. We update the value of x using the same formula as Newton, but we're plugging in our guess for the Hessian. And then at the next step, we have to update our guess for the Hessian using information from the gradient. So we calculate the gradient at the next point, and then calculate the change in the gradient, and then there's just a formula for updating our guess for the Hessian. So this can work pretty well. So the nice thing about this is, as opposed to gradient descent, this can modify the search direction and tell you how far to search, but it's only an approximation to Newton's method. The one that we're going to spend a bit more time talking about is called Fisher scoring. So this is another case where we replace the Hessian with something, and we're going to replace it with a quantity called the Fisher information. So what is the Fisher information, and what does Fisher scoring do? This is a method that can be applied to maximum likelihood problems. And here's how it works. We have a data set, y1 to yn. These are responses. And then we have a model for yi, and I'm representing that with the random variable capital Yi. And for this presentation, we're assuming that the observations are independent of one another, although that's not necessary to use Fisher scoring, but here we will. So I'm saying capital Yi is independent, and I'm representing the probability distribution with its probability density function, P, or it could be probability mass function, with argument z and parameters theta 1 up to theta p, which will stack in a vector called theta. Now, if the model is independent, then the log likelihood is just the sum of the individual log likelihoods. And to evaluate the log likelihood, we plug in the data, yi. The gradient of this is defined as gradient L theta. That's just since the derivative is a linear function, you pull it inside the sum. So this is just the sum of the gradients of the individual log likelihoods. And then our random variable version of the gradient takes the gradient formula but plugs in the capital Yi. And then the Fisher information is defined in the following way. So this is a random vector. In this case, it's going to be a p by 1 vector. And we define the Fisher information as the outer product of that vector with itself. So the Fisher information is a p by p matrix. And the ij entry is the expected value of the ith entry of the random gradient and the jth entry of the random gradient. So that's just the formula. And then Fisher scoring is very simple. It works just like Newton's method, except we're going to replace the Hessian matrix with the Fisher information matrix. Now we're trying to maximize the log likelihood, which is equivalent to minimizing the negative log likelihood. So for the gradient, we're going to put in the negative of the gradient of the likelihood, log likelihood. Okay, so that's it. It's very simple to describe. It's basically Newton's method applied to the log likelihood function or the negative log likelihood function and replacing the Hessian matrix with the Fisher information matrix. So why would you do this? In many cases, it's computationally demanding or analytically demanding to calculate the second derivative matrix. And it's often simpler to compute the Fisher information matrix. Okay, so let's see this in an example. The example we're going to do here is Poisson regression. So this is just like regular regression, except we're going to model the responses not as normal, but with a Poisson distribution. And the log of the mean of the Poisson distribution is going to be a linear function of a covariate. So our responses are counts for the Poisson, y1 up to yn. So these are non-negative integers. We have one covariate in this example, although you could have multiple covariates. And our model is the following. yi are independent Poisson, and the mean of the Poisson distribution, which is usually written as lambda, is equal to e to the b0 plus b1 xi. So we get to observe the xi's, and of course we get to observe the responses. And our goal is to estimate the relationship between the covariates and the expected responses, namely b0 and b1. So those are the two parameters we want to estimate. Now the probability mass function for the Poisson is the following. So lowercase p, z. So z is going to be a non-negative integer. It's going to depend also on the unknown parameters, b0 and b1. And we write it this way, probability yi equals z. And you may remember this formula. It's like lambda to the z, e to the minus lambda over z factorial. If we take the log of that, we get and plug in. So this is the log likelihood of the ith observation. So we're plugging in yi here. So taking the log, plugging in yi, we get yi times b0 plus b1 xi. That's from this term. And then we get a minus the stuff inside the exponential. And then a minus log yi factorial. If we take the gradient, that means we take this expression and take the gradient with respect to b0, that goes in the first entry, and then the derivative with respect to b1, that goes in the second entry. So doing b0, so this term, only thing that's going to survive is yi, and then this term you're going to get a minus e to the stuff inside, multiplied by 1. Taking derivatives, and this one goes away. Taking derivatives with respect to b1, you'll get yi times xi here. And here you get e to this stuff times xi. So that's this. And this goes away because that doesn't depend on b0 or b1. The log likelihood function is just the sum of these things over I. So this is the following. So that's the first thing we need for the Fisher scoring algorithm. Of course, we're going to take the negative of this because we want to minimize the negative log likelihood. Now for the next piece, we have to get the Fisher information. And the first step to that is looking at the random variable version of the log likelihood. So I'm just taking this formula and I'm plugging it in capital YI's for lowercase yi's. And then the Fisher information involves computing the outer product of this gradient with itself. So this is a 2x1 vector, so the outer product is going to be a 2x2 matrix. And then the Fisher information is going to be the expected value of that product. So let's just write out that outer product. So the 1,1 entry, and this is too big to put in a 2x2 matrix. So I'm just writing out each of the 4 entries. The 1,1 entry is this times itself. So that's this times this. The 2, 1 entry is this times this, so that's that. The 1, 2 entry is the same, and the 2, 2 entry is this times itself. Now this looks very complicated. Basically, so this is going to be a double sum over I and j, and then we have to take the expected value of that. But it's actually simpler than it looks because of the independence assumption. So let's look at yi and yj. So if I is not equal to j, so that's what these two lines are. I'm assuming in these two lines I is not equal to j. So this is the term corresponding to I and j. And if I is not equal to j, then we can split apart the expected value of the product because of the independence assumption. And then if you look at what happens here, we know that expected value of yi is this quantity, the mean, and expected value of yj is this quantity here. So this should say j actually. But you can see everything's going to cancel nicely. So this term cancels with that, and then that term cancels with that. So in this double sum, all of the I not equal to j terms go away, and you only have to worry about the terms for which I equals j. So the expected value of this becomes just a single sum where you're squaring each individual term. So this comes from the square of this term. So yi squared minus 2yi to the b0 plus b1xi plus e to the 2b0 plus 2b1xi. So that's what this is. And these are the four terms. So basically it's just the second one is the first one times xi each time. That's the same as the second one. And the 2, 2 entry is the same as this, except multiplied by xi squared each time. So you can verify that, but this is the formula. And this is actually simpler than it looks. So this is the answer over here, and I want to show you why that's the answer. So remember that this is true. And I'm looking at this quantity here. So I'm taking the expected value of that. We have this thing, so this is like the expected value of the square, so that's a little strange. So let's put that aside for a second. But if we look at the other terms, we're going to get minus 2e expected value of yi. So this is equal to this, so you just square this. And then you have this hanging on at the end. And now you're left with minus 2 times something plus the something. So this becomes minus the something. And remember that this is the square of e to the b0 plus b1xi. So this is the square of expected value of yi. And so we're left with expected value of the square of yi minus the square of the expected value of yi. Well, that's just the definition of the variance. And because of the special property of Poisson, is that the variance of the random variable equals its mean, then we know that the variance is equal to this. So in deriving this right-hand side over here, I'm just applying these few operations, and I find that this thing is equal to this thing. And then the other ones, this is just xi times the same thing, xi times the same thing, and xi squared times the same thing. So that's how you get so this are the entries of the 2x2 matrix for the Fisher information. So there's a lot of calculus and probability to work out what the Fisher information is, but once you've worked it out, then you have it, and you can just use it in the computations. So for Poisson regression, we just apply the Fisher scoring updates to the parameters, and but we had to derive what the gradient of the log likelihood was and what the Fisher information is. Okay, so that's it for optimization. So Fisher scoring is really useful for maximum likelihood estimation, and it's used in R in the GLM function to estimate generalized linear models.